So the goal of the talk is to propose a distribution problem in topology, which is motivated by some similar problems in number theory, and is based on my joint work with Wang Shicheng, Wang Zhongzi, and with Hang Yin. So first, let me give some examples. So we will first touch 3 examples. The first distribution problem is about the model V ranks of elliptic curves in a quadratic family. So if you fix AB and the letters n varies, you can ask how the model V rank changes when n varies. And the second distribution problem is given a positive non-square integer d, then you can think about this negative Pell equation, x squared minus dy squared equals -1. And so we wanted to say how this is solvable, if the equation is solvable for some d. So for which kinds of d, the equation is solvable. So there is some obvious necessary condition. For example, this d cannot contain the prime, which is congruent to 3 mod 4. If you mod that prime, you get a contradiction on both sides. And the third one is the topology problem. So we call a manifold is achiral. If the manifold is orientation, and if it is connected, then it has 2 orientations. So we want to know if there is a homomorphism to change these 2 orientations. And the manifold is related to the first problems is like this. So this is 3-dimensional manifold. T is a torus of 2-dimensional, and times 0 and 1 is the interval, and with this relation, model relation on the boundary. So x1 is equivalent to phi x and 0, and where phi is a homomorphism of the torus. So it can be given by a matrix in SL to Z, give you a homomorphism on the T to T. So you can close this boundary. So you got this closed 3-dimensional manifold. You can ask, if this phi is in SL to Z, not just 0 to Z, then it is orientable. So you can ask, for which kinds of phi there is a homomorphism on this M phi, change the orientations, 2 orientations on this manifold. Okay, let's begin with the first example. So let E be elliptic curves over rationals. The BSD conjecture predicts the rank of the model E group equals the vanishing order of the L series. And let RE be one of the invariants, either model rank or analytic rank. So there is a basic question: how does this RE varies when E runs in a quadratic twist family? And Goldfield gave a conjecture. In both cases, half has RE equals 0, and half has RE equals 1. So for RE equals 0, basically you have there is no solution. But if RE equals 1, then the solution can be given by Hanger points. So we are interested in this conjecture. Now let's start with one example of this Goldfield conjecture, namely this congruent elliptic curve family. So this elliptic curve, like ny squared equals x minus x, x group minus x. It has a positive model V rank if and only if n is the area of a right triangle with a rational side length. For this spatial family, and the Goldfield conjecture can be reformulated as the following. So among all square-free positive integers n incongruent to 1, 2, 3, mod 8, the density has analytic rank 0 because the sign of this L function is +1. And among, if sign is negative 1, then density 1 has the rank 1. Okay, now the part 1 is known for model rank by Alex Smith. And for this analytical, I might join work with Branger through this p-converse for rank 0 case and p equals 2. And the way Alex Smith proved this Gold function for model rank is through this same rank for p equals 2. Okay, so the related distribution here has a starting point. So if you start a 2 infinity similar group, the downstairs is just a 2 similar group. And for 2 similar group, we can ask when the essential rank of 2 similar group is just 0. So that's called the first descent. So Fermat actually made this first descent to show 1 is not a congruent number. Okay, so now let n varies among this square-free positive integer congruent to 1, 2, 3, mod 8. And we can ask the 2 similar group mod, these 2 torsion points, has rank 0. And they have this property have density like this integer, or like this number. Okay, so this is theorem of Hess-Brown. Later on, Sven Dyer found this congruent number family-like family. This density also hold. So the second example is about the negative pair equation. When is d bigger than 1, non-square positive integer, we want to solve this pair equation, x squared minus dy squared plus minus 1. For a single d, this is completely solved by Langlands through continued fraction. So if you write the square root of d as a continued fractions, and it is cyclic. So say from A1 to AM is a 1 cyclic. Then you write this partial continued fraction from A0 to AM minus 1. Write it as a reduced fraction x over y. Then you know x squared minus dy squared equals negative to the m. So if this m is even, if this minimal period is odd, then the negative pair equation has solution, is solvable. But if the minimal period m is even, then the negative pair equation has no solution. But we want to know how this d distributed, if for which this negative pair equation has solution. So for example, this square root of 205, which equals 5 times 41. Both of them are congruent to 1 mod 4. So, but the minimum period is 8. So this equation has no solution. Okay, this is like an observation necessary condition for the solvability. Recently, this divergence conjecture was solved using Alex Smith's method. So let D runs over all square-free positive integers without the prime factor congruent to 3 mod 4. So where there is no, so you consider this D without local abstraction. And among those D such that the negative pair equation has solutions, has density 1 minus this product. Okay, this is our second example. And the third example is for this source 3 manifold. So recall that an orientable manifold is called achiral. if it admits an orientation reversing homomorphism. So we call a commensurable class. Commensurable class means two manifold is commensurable if they have common finite covering. Okay, a class is called achiral if it contains an achiral member. We call it spatial if it contains an non-orientable manifold. So if a class contains a non-orientable manifold, then this manifold has a classical double cover. That classical double cover is orientable and is automatically achiral. So a spatial class is automatically achiral. So this looks like to be spatial, there is some local obstruction being achiral. So we want to ask, how do spatial classes distributed among achiral classes? So for now, let's focus on this kind of manifold three-dimensional Saw given by this forest time the interval 0 to 1, and the Coulomb boundary by some matrix in SL to Z. We call it anasolve. This is the name for Saw if this phi has eigenvalue real quadratic. Okay, so the discriminant of the real quadratic field generated over Q by eigenvalues of phi is a completely invariant of the commensurable class containing M phi. So there is a one-to-one correspondence between commensurable classes of Saw manifolds and the real quadratic field. Now this is theorem. So for commensurable classes of Saw 3 manifolds ordered by discriminants, the density of spatial ones among achiral ones is again this 1 minus the product. Discriminant because this class one-to-one corresponding to real quadratic field. So discriminant means discriminant of the real quadratic field. And this three distribution phenomenon has behind the rule or law from probability. So there is a Markov chance. So here is an example. How to construct a spatial. For example, if you want to construct a non-orientable Saw manifold, you just use some 2x2 matrix with determinant negative 1. So just by definition, you know it is unorientable. So the orientation, for those, this double cover of this non-orientable band, it has an involution without a fixed point, changes the orientation. So you look consider this 2k times 2k matrix over F2. We just alternating. Alternating means this it is symmetric and with the diagonal 0. So there is a Markov chain with random variables given by this co-rank. So in this probability space with the counting measure and this co-rank random variables has this stationary distribution given by like WM, and this stationary distribution given by this number. Just means symmetric and with diagonal 0. Yeah, that's alternating means. Because in F2, 1 equals -1. Okay. Now, the point I want to say, like, what we did for quadratic, any quadratic twist family of integer curves over Q with full rational two torsion points like this. You fix E1, E2, E3, let n varies. Suppose there is no exceptional twist with this essential model two similar group 0, then the density of this with trivial two similar rank is positive. So in positive, S is a two similar group. So this is like a first descent. You get a rank 0 case. So any such family can be reformulated as like a so-called the theta congruent number family. For any theta with cosine theta rational, you look at this family, ny squared equals x minus cosine theta times x squared minus 1. So this family, and when cosine theta runs over all rationals, and so this family is the same as the families here. But there are three cases in terms of theta. One case is sine theta over 2, cosine theta over 2 are all non-rational. Both of them are quadratic. And if one is quadratic, another is rational. This is case B. If both of them are rational, this is case 3. Case C. So we divide families into 3 cases. Like a congruent number is really the first case. So Swinner-Dyer found this Markov chain in case A. So what does the Markov chain should be under this in the case A? And we got such kinds of distribution result before. But for part B and for case B and case C, for example, x not 15 is of case C. Okay, for all of these cases, they have their own Markov chain behind them. And use this and the analytic number theory, then we can prove this result. Actually, we can prove very precise density for this set. And now let me explain this condition non-exceptional twist. This non-exceptional condition just means some twist with prime factor outside the discriminant of E, the original E. So it has a linear algebra criterion over F2 and can be easily verified. Actually, long ago, Wang gave a conjecture, say, for any quadratic twist family, there is a member who has analytic P-sha favor. And then Prasad did some evidence in his thesis at Princeton. So actually, we refine Wagen's conjecture and say, so it can be formulated in this way. Anyway, so if the conductor of E minimum 1 less than 1,000, we check this condition always true. So Wagen is a heuristic holds. Okay, so basically for any quadratic family with two rational points, the two similar group being trivial has a positive probability. Okay, so this is number 3 motivation for this topology problem. Now let's come to this some details for this topology result. For this Sol 3 manifold is constructed in this way. So there is a question: can you find a commensurable class such that every member in the class is not achiral, is chiral. So first, some people asking this question. So can you find one example of classes such that every member in this class is chiral? So actually, this discriminant concept helps a lot. So if the discriminant of the real quadratic field generated by the eigenvalue of phi is divided by some prime congruent 3 mod 4, then every member in this class is chiral. So this tells you actually almost all classes are chiral, but without this observation, it's hard to say the reason. Okay, so give you the matrix phi. We have this rim-dimensional manifold M5, and we can associate this manifold this discriminant, and it's called the binary quadratic form. This binary quadratic form has discriminant D. So the primitive part of D phi is the discriminant of the real quadratic field. So this may be like D times C squared. Okay, so we found that this D phi is easy to check. It's just topology invariant of the manifold. Let's call it the discriminant of this manifold. Okay, now the key observation is the Gauss's this how to say that, the addition law among binary quadratic forms. So let D be a positive integer discriminant, and this to be the class group of discriminant D, and the co-zero is this principal form. So this M is achiral. This manifold itself is achiral if and only if this co-zero represents -1, or 2 times this Q phi represents -1. So co-zero represents -1 is just negative Bayer equation. So 2 times this Q phi, this is the Gauss's operator. It's just like a summation of ideal class. Co-zero is the principal form, just like a Bayer equation x squared minus dy squared, right? If D is congruent to 1 mod 4. And this phi is easy to okay. So this topologists describe this mapping degree set using this quadratic form and the form corresponding to negative Pell equation, and we found actually the involving result. So like this mapping degree set contains the -1 if and only if this 2 times this quadratic form can represent -1. Okay, so this is the key observation. So starting with this. So let M be a commensurable class, and M phi is a member in the class. With the Gauss's genus theory, actually we can prove this. So this is really Gauss's genus theory. So this class contains a chiral member if and only if this discriminant not divided by any prime congruent 3 mod 4. And the commensurable class whose real quadratic field has discriminant D contains a non-orientable manifold if and only if the principal form represents -1. This means negative Bayer equation has a solution. Okay, and the Gauss's genus theory tell you this necessary condition and two Pell equation having a solution namely this D is also divisible by any prime common to 3 mod 4 is equivalent to this achirality. Okay, so from these two property, then we know the third result comes from the Stevens conjecture on distribution of solvable negative Pell equation. Okay, so this is the proof of topology result. But after this, you may ask, if we replace this solvable manifold by others, so what kinds of number theory can come into the picture? You can ask the same question. So for example, like this H3, this is three-dimensional hyperbolic manifold, and if you mod some discrete subgroup PSL to C, and suppose you get a closed manifold, let's call it a hyperbolic string manifold, and you can associate this kind of manifold quaternion algebra B over K, and if this quaternion algebra, we view this K as a subfield of C, so there is a complex conjugation. If the quaternion algebra is invariant under the complex conjugation, then we call it a base change. Then it is a base change from like a smaller number field. But if it's not the case, then again, the commensurable classes of this manifold contains no achiral members. So also a number theory reason can tell you there are actually almost all classes of hyperbolic three manifolds are achiral. So anyway, we can ask the distribution of spatial commensurable classes among achiral ones for topology manifold with fixed geometric model. So you can ask this general question. So this to propose this question is our main goal of this talk. And if you look at this source, the 8 geometries in 3-dimensional, there are 8 cases. So for this first 6 cases, there are only 1 commensurable classes, and it's easy to say which one is which case is achiral, which case is spatial. So this question for these 6 ones is easy, and the first task is to start the SOA and the hyperbolic. So we already know what's the distribution result for SOA. Now we can ask how achiral. So we look at SOA is the torus bundle over S1, right? Or you think about all the torus bundle over S1. If the Goodwin matrix has a real periodic as an eigenvalue, then we call it SOA. So you look at all this is real eigenvalue. Real eigenvalue means because the product is 1, so 1 is bigger than 1, the other is less than 1, right? So the SOA, the allosolve phenomenon occurs there. So among all those manifold, there are this product of this number 1 minus 2 to negative j to the negative 1. So for this proportion has spatial property, contains non-orientable member. Okay. Okay, now the result for this H3 is quite different. So for all commensurable classes of hyperbolic string manifold, if it is achiral, then it is spatial. What? S3 is achiral. Oh, this is very simple. So you put S3 into R4, right? Then you look at this, there is a three-dimensional hyperplane. There is one-dimensional is normal vector. So you just map Z to negative Z and keep the other three coordinate same. This is reflection along this hyperplane in R4. So you put R3 or S3 into four-dimensional, right? So four-dimensional ordinate space, and you use this reflection with respect to this R3, this hyperplane. You get a homeomorphism change orientation. And if you want to say this R3, this any manifold with model S3, for example, name space is non-spatial. So you can use this kind of argument if it is spatial. If it is non-orientable, then you look at this double cover. The double cover, the double has a convolution, evolution of order 2, and changes the orientation, and also without a fixed point. Now you lifting this evolution into S3, this universal covering space, and there are also evolution of order 2, change orientation, and without a fixed point. Now you apply this Lipschitz fixed point theorem, because H2, H1 are 0, so there are only H3 and H0, both of the isomorphic to Z. So H0 give you trace 1, H3 give you trace negative 1. So negative 1 plus 1 equals 0, but the summation H3 how to say it? So this orientation give negative 1, but you should times negative 1 again because 3 is odd. So you get there are two fixed points. But our assumption is without fixed point. Okay, so it's very easy to prove there is no three-dimensional space modeled on S3, which is non-orientable. Okay, anyway, so now the main problem is about the SO and H cube. But for H cube, the distribution problem is completely different. Like each achiral one is spatial. So if the class contains achiral manifold, must contains non-orientable manifold. Now look at this H3. So this isometric group of H3 with keeping the orientation is isometric PSL2C. And without requiring keeping orientation is like is extension of SL2C with by this order 2 group generated by complex conjugation. So this complex conjugation change orientation. And it is useful to extend the whole category to orbifold. So, and with fat volume. So this is a hyperbolic geometry. It's very useful to think about to enlarge your category. Now, when I say achiral gamma 0, it means the corresponding quotient of gamma 0, H3 by gamma 0 is achiral. So given a achiral discrete subgroup gamma 0 of this isometric of H3, consider its normalizer. Because gamma 0 is achiral, then the normalizer must contains the elements and projecting to top the complex conjugation. The top, then you get a non-orientable orbifold. And our goal is to say if you start with a chiral class, they say gamma 0, and if you only think about the manifold, then you try to find a non-orientable element, like a manifold in the class. And the natural candidate is the one corresponding to the normalizer of gamma 0. But the trouble is gamma, this normalizer may have torsion, so that the quotient become to orbifold is not a manifold. So our main goal is to find a torsion-free subgroup in this gamma, which contains an element mapping to the complex conjugation tau. If you have such a torsion-free subgroup, then the corresponding hyperbolic straight manifold is non-orientable manifold. Now this question is a pure number theory question. So first, let's say the topology can give us some input. The first input is by they call it the rigidity principle. This normalizer contains this gamma 0, but the index is finite. If the index is finite, then gamma 0 and the gamma are commuable. They corresponding to two manifolds. They are commuable. They have common, they have finite covering. So this is the first input. And the second one, if you take a trace of the gamma joined to Q, then you get a number field. And because we started with some gamma 0 or gamma, this doesn't matter which one you use. And this K cannot contain in R. So it has at least one place, infinite place complex. And if you join this gamma itself, not only just trace, to the K again, then you get a quaternion algebra. And this quaternion algebra is defined over K. If we assume our gamma 0 is a chiral, then this quaternion algebra is the base change from the fixing field of the complex conjugation. So this will also tell you, this is what I said at the beginning of this hyperbolic case. So almost all hyperbolic straight manifold are chiral, not achiral. Okay, now you have this gamma, this normalizer of gamma 0, which contains the element project to tau, is corresponding to non-orientable property. So it is a group. It is a discrete group of B cross, BK cross, mod K cross. So like a PB cross, and the semi product with one at the top. So this is all input from topology. Then we can make an abstract situation like in number theory. Suppose I give you a finite Galois extension of number field with Galois group delta. And if I give you a G, this connected algebraic group defined over F, which is absolutely simple and also adjoint. So like a PB cross. Suppose you have a gamma contains in GK semi-product of delta, which is further generated subgroup such that the following three conditions holds. First one, this gamma 0, and this is the G component, this the gamma intersection with GK is darkly dense in G. And also this projection from gamma to delta is surjective. Like in the previous concrete situation, you have elements mapping to the complex conjugation so that the corresponding orbifold is non-orientable. And third condition is no non-trivial elements in delta X trivially on gamma 0. So you have this. So if you have this, if the delta is cyclical of prime order, then you can find there is a torsion-free subgroup of gamma, which which is non-orientable. Say, like a surjective has with surjective projection to delta. So to find this, to prove this, every achiral class is spatial, as I said, is equivalent to found a discrete subgroup PSL2C, or say this PB class without torsion elements, and contains elements surjective projected to this complex conjugation. Now, this is a little bit more general situation for that requirement, but this is the hold if delta has a prime order. So they prove just like a little trick, choosing some prime of F split in K, and using this strong approximation theorem to find this gamma prime. Now this strong approximation theorem involving here is a little bit more general than what we did in what we have in number theory. So in number theory, if we have a simple group, then we know the rational points is dense in the others. But here, if you sometimes we want this G to be adjoint, so not simple. And the original strong approach theorem is for this simple one. Then you can ask you the general question. Suppose I give you a reductive group whose center is finite, and you want to say the k Russian points, the position of the closure of its Russian points in its others. So what this should be? Okay. Now the theorem says like this: if I give you a absolutely simple adjoint algebraic group over number field, and if this it contains the discrete subgroup gamma 0, which is federated, largely dense, such that this K is the minimal defining field. Minimal defining field just means you cannot find any subfield of K, such that gamma 0 is contained in E point of G. Then you can think about this general commutator from GK cross GK to GK. But this commutator map can lift into this universal covering, which is simple G tilde. So let's call this, let's denote it as again this bracket as this commutator to the simple one, right? Now this universal covering is simple. And the theorem says the closure of this commutator on gamma 0 is open in this simple member, the identical partial identical point for some fat set of places S. Okay, so this is like a main reason for this spatial property in hyperbolic three manifold case. Now you can think about the more general case. How about for any geometric model? You can ask, if you fix any geometric model, you look at all this achiral commensurable classes to see how spatial one distributed. Okay. So the first thing is this Lie group theory will tell you how you mixed this Saw type and hyperbolic type together. Okay. Okay. So if we fix like a geometric model, like a Saw Lie group or this PSL2C, right? Then you can look at all manifolds with this model. Okay, so let's fix geometric model, look at all commensurable classes with this model. We already gave us two examples, right? Saw or hyperbolic three manifold. So among all these commensurable classes, you want to understand the distribution of spatial one among archival one. There is non-orientable member. Yes, if you use, so the commensurable class means the spatial class, there is non-orientable one. And archival means there is a archival one. Right? So one class, so the spatial class is automatically archival because it's double cover belong to the same class and which is archival. So looks like in number theory, we have local condition. You want to ask some global property, how distributed the scientists find these local conditions. Oh, you mean even for this manifold, you want to construct some object, which is not a manifold. Yeah, I think about this question. Even not even topologists doesn't care. So yeah, for example, I just replace phi belong to S or to C, replace this Z by any the ring of integers of function field. Then you can ask the same question. Right? But besides this general case may mix this soul type and hyperbolic type together. But there is like this probability equals 1 minus this product, like a negative variable equation. So there are only like a positive proportion of these spatial ones in among archival ones. But for hyperbolic, you just get 100%. And if we look at higher cases for this Saul case, for this hyperbolic case, so we expect a similar result to the hold. And the reason maybe is similar to the before. But the interesting thing is the second one. If you think about this Saul manifold of high dimensional, say like over total real field with even degree or with even degree over Q. So this Hezbollah and Hezbollah consider those manifold and made a conjecture about the property of this Saul manifold over with respect to high degree or general degree over total field with general degree, even degree. So that case, that conjecture was solved by Atiyah, Singer, and so on. And if you look at those examples of Saul manifold of high dimensional, then this corresponds to total real field with higher degree. For example, let's just look at the degree 4. So beside 2, the next one is 4. And it requires the Galois group of F over Q, just Z over 2Z times Z over 2Z. Then the analytic number 3 becomes much more complicated. So now there is a corresponding number theoretical question. For example, let F be a totally real field, Galois over Q, for example. Then we can define a sort of narrow ideal class. But their narrow just means we mod this relation of this principal idea and this generator X will require just norm bigger than 0. Not every place is bigger than 0, just norm bigger than 0. And you associate only in this narrow ideal class and a group of totally positive units, then you can construct a Saul manifold of dimension, say this, if this degree is 2, This degree of f is 2, then you get a 3-dimensional. If the degree is 4, you get a 7-dimensional. What? Sigma is some elements in the Galois group. So if then the associated Soul manifold is achiral, if and only if this class times this divided by this sigma x on this ideal class, you get it is generated by some theta, and this theta has negative norm. So in this narrow ideal class, this theta, even if it is a principal idea, but it is not trivial. So achiral corresponds to this property. And again, the spatial corresponding to it has a negative norm unit. So you can ask the same question. When among this achiral property, how this totally real field with norm has unit with norm -1 distributed? You can answer this question. But this question becomes true. So this if you start this distribution problem, this analytic number theory part becomes very difficult for this higher dimensional. Even you just think about the degree 4 instead of degree 2. Okay, so this gives you many new questions in number theory from topology, right? So you can think about this distribution of total real field, satisfy these two kinds of property, how distributed of the ones with this negative norm unit among those with this 1 sigma x on this ideal class equals the unique class theta. Okay, so this is so my talk just want to formulate to propose this kind of distribution problem in topology about the orientation. Thank you very much.
For the beautiful talk, are there questions?
Remarks and trying to find order. S, right? F and I.
So you let F runs over all total real field.
Yes.
Which is Galois over Q, and for example, with this Galois group. And then you think about the distribution problem of those who have negative norm unit. So the unit has norm 1, -1. Among those has this kind of property. So who has a narrow ideal class, which satisfying 1 sigma x on this ideal class equals the spatial class.
Condition in the biquadratic.
Anyone, this is just example. I just say this is a very simple example is already complicated. It's already difficult or complicated. Of course, you can fix this H2 ending group. What? Okay, so why people care this stuff?
Maybe
yeah,
you give some history. What's exactly going on?
So why we take care of integers? Because you can count, right? And in topology, if you think about all closed manifold, it's actually countable. So you can also think about the counting problem in topology. But those guys maybe didn't think about this question before. So when I read this paper of these topologists, and they gave me some result. This result looks like a pair equation is there, and the quadratic form is there. So like a Gauss stuff is already there, but they didn't think about the number theory inside this kind of phenomenon. So I tried to figure out. At the end, I found just Gauss genius theory exactly gave you this situation. So let me say this following. If clay bottle can be discovered before Lagrange, I think this kind of thinking replace J2 equivalence by SL2 equivalence by Gauss could be happen earlier than Gauss. Because this kind of problem, like about the orientation, can give you motivation to think about this equivalent classes of binary periodic form, and like with equivalent at the beginning by GL2Z, right? Because they wanted to say how the periodic form represents which kinds of integers. So of course it is equivalent under GL2Z. But there you cannot do addition. So Lagrange and the round cannot make this perfectly. So later on, Gauss used SL2 equivalence to do it. But if you know this problem earlier, then you can do this naturally, get this SL2Z equivalence to introduce this ideal class group, other class group, like what Gauss did. So anyway, this is new problem in topology, but I think it's interesting. Like many number series stuff coming to
So
the
you say that it's by definition, right? You know, like the these manifolds are discrete, so they don't have a nature invariant attached to it. I saw somebody say it's a well,
If it's for any manifold, is
I
any
saw that the volume that sounds something to do with the special value functions.
oh, you mean that? So for this Saul manifold, there is a conjecture given by Hertzberg, and he relates this L value of Schmidt L function to some topology invariant called the signature defect. So that one, like so for that one, this Schmidt-Weyl function of M phi with 0 equals the signature defect of M, right? Now, for this one, maybe you're also interested in, like, first of all, we know this L series by S, right? Like in this three-dimensional case, is identically 0 if and only if phi is achiral, M is achiral. And if not, so if not achiral, then this L function is complete invariant of, then is complete invariant of this M phi. So it is either identically 0. It's not the L function of motive, it's a combination. But if it is not achiral, then it is complete invariant. Then you can understand this Taylor expansion of this entire L function of M phi, like n's derivative divided n to the power s n, right? You can think about this Taylor series. Now the similar question as Wei Zhang and Zhi Yin, you can ask, what's the topological meaning of this one? So we found some evidence for derivative, like use your work with Xin Yi.
That's a good answer.
So this is maybe like a number theory like it.
So achiral, then you have a what is the complete invariant? Can you say it again?
Complete invariant means
For that one, for achiral, right? You say it's vanished, then you don't.
if it is achiral, then it's identically there. Oh, for this one,
Say classified.
so this kind of stuff is very few. As my talk is very few. So for this kind of stuff, we try to solve the question about this distribution. And for Kyle one, this is just the analysis, topological analysis.
Thank you.
So just a question about just a very naive question. If I extend my the commensurability classes and include all the folds, I'm guessing the analysis is going to be more complicated because now you have to involve the torsion. But do you have enough understanding and control of the torsion to get bounds on the probability?
I tried to think about this. I didn't get a result.
And can you also go back, or can you explain a little bit more about the characterization or the B over K condition for the hyperbolic case? I didn't quite understand it.
So this so gave you this discrete subgroup of this PS to C, right? Then you can form this this manifold M gamma, this hyperbolic one. And how do you form number theory here? So there is a so-called invariant number field and the invariant quaternion algebra come from this gamma. Okay, the first one you just join all trace of gamma into Q. And this one you just join all gamma there.
What was
And
the second one?
Huh?
What was the second one?
So the second one is you just join all gamma inside the K, because everything is in this M2C, this algebra, right? So you think about this B, K, and B, all are sub-algebra of M2C.
Ah,
And this topology input tell you the rigidity, tell you this number field. This is a quaternion algebra.
okay, okay.
Okay, but the quaternion algebra has the ramified places, right? So you look at the ramified places S, and the complex conjugation acts on this. If it is invariant under this complex conjugation, then this gives you achiral ones.
Yeah, okay.
Okay, but there are so many quaternion algebra, not achiral, because it's just a product of some primes, right? If the prime is not a, so this ramified places of B. If what we just a product, just like a set of primes. If the set of primes is not invariant on the complex conjugation, then it's automatically not achiral. So this non-achiral is almost all non-achiral. Of course, S is determined by this is the invariant of the manifold. Of course, S is invariant of B. Gamma discrete subgroup of PSL2C. Huh? Identical. Oh, there are the two cases. So if gamma is arithmetic, then we call it arithmetic hyper three-dimensional manifold. But there are many non-arithmetic ones.
It can also be.
So if it is arithmetic, then this K is almost totally real. It has one places complex, and all the other infinite places are real. But in general, it's not. Definition of this
Function.
This is Schmidt's error function catches the. So when Schmidt want to compute the number of Hilbert module forms, so he introduced these error functions.
So what's that? Can you write it?
Yes. So if there is a way to write down like a user idea, so give you I, give you this this I is the idea of OF. I give you a U contains in your F plus totally positive. Then you can associate this M IU like my M phi. You can write phi as in terms of I and U. Then this error function of M phi S equals the summation of norm of how to say that? Norm of X to the sign of norm of X. X belongs to I, but not 0, and So this definition,
Partial.
this is a combination of Artin error functions.
Yes.
And actually this error function is same as the error function show up in average columns, like the parity.
Okay, so there's no further question. Let's thank speaker again. And we resume at 45.